Hello everyone, welcome to the another session. In this video, I'm going to discuss about the properties of inner and outer product. In the discussion related to the brand kit notation, we just discussed about the inner product and outer product. In this video, I'm going to discuss about the properties related to the inner and outer. For example, if the psi is a state vector, here it is represented as ket psi is a state vector. The conjugate transpose is take it as like a bra vector. This is the ket, it is the bra. So the inner product between these two, this is called as inner product. For example, in mathematical way, the psi is take it as like a row matrix, and this I will take it as this is a column matrix and this is a row matrix. The product between these two, here the first one is like bra and ket. So A into A star plus B into B star. This gives like a value. Thus, this is also called as scalar. So the conclusion is the inner product between the two state vectors gives the result in terms of scalar. So the inner product yields a scalar value. This is the first property related to the inner product. Second one, conjugate symmetry. Conjugate symmetry. The meaning of conjugate symmetry is, for example, just you take the inner product between the two state vectors like phi and psi, which is equivalent to, after swapping it, the psi and phi is a complex. So here the inner product between the two state vectors is equivalent to the complex conjugate of after swapping the two state vectors. And then positive definites. For example, if the state vector psi and psi inner product is 0, if the state vector psi is equivalent to 0 state vector. Otherwise, if the psi is the 0 state vector, then the inner product is 0. Otherwise, always the inner product between the psi and psi is greater than 0. And a condition like this is called as positive definites. And a normalization condition. Normalization. Every state vector ket psi satisfies the normalization condition, that is the inner product between the same state vectors is always equivalent to 1. This is the normalization condition. And then orthogonal. How we can check whether these two state vectors are perpendicular or orthogonal each other. If that I just consider the two state vectors phi and psi. or psi1 psi2. Now I am checking the whether these two are orthogonal or not. I'm just take it as like a inner product between the phi and psi. If it is equivalence to 0, this is called as orthogonal. If it is mutually perpendicular to each other, then inner product is 0. So orthonormality condition. How we check orthonormality for the two state vectors? For example, I just take the inner product between the two state vectors. One is representing the psi I and psi j. If we assume I equivalents to 0, that means same state vectors, it is equivalents to 1. If I not equivalents to j, then this value is equivalents to 0. The same state normalized, different state orthogonal. So this is called as orthonormality conditions. So this is about the properties relate to the inner product, like scalar value. The inner product always produces the scalar value, conjugate symmetry. The psi and psi inner product is 0 only when the psi is a 0 state vector. Normalization, that is psi itself psi, that means inner product if you take, its value is 1. If two different state vectors product is 0, then these two state vectors are called as orthogonal. So orthonormality means if inner product between the psi and psi j, if I equivalents to j, it is equivalents to 1, and if I not equivalents to j, this is equivalents to 0. This condition is called as orthonormality. And coming to the outer product. Outer product between the two state vectors. This is the representation for the outer product. For example, I just take the mathematical representation. Here, this is like ket. This is like another parameter, bra. So here, column matrix is a row matrix. Just see here. This is like multiplying like a 2 by 1 matrix with the 1 by 2 matrix. The resultant is 2 by 2 matrix. Here the result like A into C, A into D, B into C, and B into D. So this is like, it won't give the scalar value. It is giving like another different matrix. So outer product is not giving the scalar value. Outer product is gives like an operator. It acts like an operator. You may have doubt if what is the meaning of operator. For example, in mathematics, d by dx of sin x. Sin x is a function. We just operate with certain operator that is called as differential operator. The function changed to the cos x. The function is transformed or changed to the other function by operating with certain operator. Similarly, outer product is act like a operator. So for example, here this operator, that is the function like outer product, is operate on the function like xi, which is equivalence to this is the phi. Now in between the inner product between these psi and chi, as we know that inner product gives the scalar value like k, then it transforms the function like k into phi. So when we are operating with the outer product operator on particular function, then it change the function to the other with certain multiplication parameter. So outer product is act like a operator. Here also adjoint relation, that is when we taking the outer product between the two state vectors, which is equivalence to, after swapping it, this is a swapping parameter, it is equivalence to Hermitian. The Hermitian conjugate of the outer product, a Hermitian conjugate of the outer product of two state vectors is equal to the product of the same two state vectors after swapping it. Same here, after swapping, here it is the Hermitian conjugate. In this, it is the first one is the phi. In this, the second one is the phi. So after swapping the values, which is equivalence to Hermitian conjugate of the outer product. And completeness relation, it is most important. Completeness relation, this can be discussed in detail in the other aspect also. Completeness relation, a set of orthonormal basis states, like we have orthonormal base states, is said to be complete. Eppudantamu complete is said to be complete if and only if, or if any state in the Hilbert space, it can be expressed. If it is complete, that means that it can be expressed as a linear combination of, which is equivalence to I, identity matrix. Sigma, linear combination of outer products, which is equivalence to I. I think you will get more clarity by seeing this result. For example, I just take the two state vectors 0 and 1. 0, mathematical way we can represent as 1 0, and the state vector 1 is represented as 0 and 1. Similarly, the bra 0, which is nothing but 1 0. Similarly, the bra 1 is also 0 1. So as we discussed, these are the two state vectors. When we can take it as like a completeness, we need to take the linear combination sigma. Sigma means like a summation. 0 outer product. Similarly, 1 outer product must be equivalence to I, identity matrix. So by just see here, multiply all these factors. This is a ket 0, 1 0, sorry, 1 0 plus 0 1 0. By multiplying these two, we'll get like 1 0 0 0 plus 0 0 0 1, which is equivalence to 1 0 0 1. So which is equivalence to identity matrix. Then we can conclude that the psi, therefore the psi can be written as, this is like identity matrix. That's what I just write it as plus into psi, because this is like there is no transformation. Psi is equivalence to identity matrix. It's like an operator. There is no change because operator is like an identity, which is operate on the psi, that itself gives the same result. So if this is the case, then we can call it as completeness relation. So in case of properties related to the outer product, it's not a scalar value, it is an operator. Outer product is always gives the operator. And action, if it operates on the particular function, a state vector psi, it changes to the other state. Hermitian conjugate of the outer product of two state vectors is equal to the outer product of these same two state vectors after swapping the bra and ket. It is act like a projection operator, and completeness relation is as like this.